Hi everyone. So this time we're going to solve one of the most difficult integrals that you will find in your calculus exams, and that integral is the square root of tan x dx. Alright, at first glance it may look like this integral is straightforward to solve because we only have one term here, but the fact that this term is being affected by a square root is something that makes things a little bit more challenging. So one first thing I can do here is I can apply a substitution where tan of x with the square root of tan x is equal to u, and what this implies is that tan of x is equal to u squared. Okay, so if I apply derivatives to each side of this equation, what I will get is the following. On the left, I will have the derivative of tan of x in this case is sec squared of x. So I'm going to write it down here. So sec squared of x dx is equal to, and on this other side of the equation I will have 2u du. Alright, if I look at the original integral, I have two terms here. First I have the square root of tan x, and then I have the dx here. I need to make these two terms be function of u, which is the new substitution I'm making here. What do I need to do for that purpose is I need to find what the values of square root of tan of x will be, as well as dx. But if I solve for dx straight away here, what I will find is that dx will still be a function of sec squared of x. So I need to find a way for me to make dx be only a function of u, which is the new substitution I'm making here. So what can I do in order to achieve that purpose? I know by trigonometric definition that sec squared of x is equal to 1 plus tan squared of x. Dx is equal to u du. Alright, things are starting to look better here. I know by the original substitution I made that tan of x is equal to u squared. So if I replace that in this term that is inside of the parentheses here, what I will get is the following. So let's do that. This is going to be 1 plus u to the fourth dx is equal to 2u du. Alright, now let's do what I'm looking for here. I need to solve for dx, and dx is equal to 2u du, and this other term is going to the other side as a division, so that is u to the fourth plus 1. Okay, so what I'm gonna do right now is I'm going to replace these two terms in the original integral. First the square root of tan x, and then dx. Let's do that. So and just for convenience, I'm just going to name this integral I, so I can reference it later. So I for me is going to be integral of a square root of tan x, but the square root of tan x is simply u. So I have u here, and dx is this new expression I found. So let's get that replaced here. That is going to be 2u du over u to the fourth plus 1. So let's organize the terms inside of the integral here. I can get the 2 out of the integral, so that should be 2 of integral. Okay, this u with this u will be u squared du over u to the fourth plus 1. Right. And just for convenience, I'm going to name this integral I1, and from now on I'm just going to focus on solving this integral here. Okay, so what strategies can I use here in order to get I1 solved? First thing, I'm going to restate that integral here. I'm going to say that I1 is equal to integral of u squared du over u to the fourth plus 1. Okay, one first thing I can do is I can factorize the term that I have here in the denominator of this expression. And okay, let's focus on that term first. I'm going to restate that term. So u to the fourth plus 1 can also be expressed like this: u squared plus 1. So why am I doing this right now is because I want to make this term look like a squared binomial. So in order to do that, what I'm going to need to do here is I'm going to add and subtract some terms so I can achieve that particular purpose. So if I do this, u squared, and if I add to u squared plus 1, since I am adding this new term to u squared, I also need to subtract that term. So I will set it to 2u squared. Alright, so what you can see immediately here is that this first part of this expression can also be written like this. That is going to be equal to u squared plus 1 squared minus, and this other term here can also be written like this: square root of 2u squared. Alright, as you can see, this expression pretty much reminds me of something that many of us already know, which is the expression that corresponds to a difference of two squared variables. So for example, if I have a squared minus b squared, what I will have is that this can be factorized like this: a plus b multiplied by a minus b. In my case, a is going to be equal to u squared plus 1, and b is going to be equal to square root of 2u. So, okay. Given that condition, what I can do is I can write u square root of u squared plus 1 squared minus square root of 2u squared can also be written like this. So a for me is going to be u squared plus 1. Let's just write it down. Plus b, and b is for me square root of 2u. So, okay. And the other term, a minus b, should be u squared plus 1 minus square root of 2u. Okay, so I have achieved exactly what I was looking for. I needed to find an expression that is a factorization of the term that I have here in the denominator of this integral. So if I replace this here, what I will get is the following. So I1 is going to be equal to integral of u squared du over this expression I just found, but factorizing. So let's do that. U squared plus square root of 2 u plus 1 u squared minus square root of 2 u plus 1. Alright, so after factorizing the denominator, what I can go ahead and do is I can express this integral as a sum of two fractions. So what that means is that this integral can also be expressed as a decomposition of this form. That should be the integral of au plus b, and in the denominator of this first fraction I should have what is inside of the first parenthesis here, which is u squared plus square root of 2 plus 1 plus, and I should have another fraction whose denominator looks like cu plus d, and whose denominator is what I have inside of the second parenthesis here, which is u squared minus the square root of 2 u plus 1 du. So this is a decomposition in partial fractions of the expression I have here on the left. Well, as you can see immediately, now I have four unknowns, which are a, b, c, and d. I need to solve for these coefficients now. So what I have to do at this moment is I need to create an equation system of four equations that will also have four unknowns, a, b, c, and d respectively. How am I going to come up with that? Okay, the intuition here is that if I operate on these two fractions, what I will have is that the denominator of the second fraction will multiply the numerator of the first fraction, and the denominator of the first fraction will multiply the numerator of the second fraction. And after making that operation, I should have something that is equal to u squared. Okay? So let's continue with this. I will say that au plus b, which is the numerator of the first fraction, multiplied by the denominator of the second fraction, u squared minus the square root of 2 u plus 1 plus cu plus d, which is the numerator of the second fraction, multiplied by this u squared plus square root of 2 u plus 1 should be equal to what I have here on the left, and that is u squared. Okay, so what I need to do right now is I need to develop these two expressions, so let's do that. Okay, so this is going to be a u multiplied by this is u to the third, and here I will have minus a square root of 2 u squared, so this and this, plus a u. Now let's do the same thing for b. So this is b u squared minus b square root of 2 u plus b. Okay, so I have already dealt with this first part of this expression. Let's do the same thing here. So cu and u squared, that is cu to the third plus c square root of 2 u squared plus cu. Now let's do the same thing for d here, and that is plus d u squared plus d square root of 2 u plus d. So all of this is equal to u squared. All right. So let's group these terms together by using their corresponding common factor. Let's do that for u to the third, for u squared, for u, and so on and so forth. So let's focus first on the terms that have u to the third here. A first term is this one, and then later I have this one as well. So terms that have u squared, one of those terms is this one, another one is this one, then I have this, then I have this. Now terms that have u's only, a first term is this, another one is this, then I have this one, and finally this one. And the independent terms are b and d only here. So let's just mark those. All right. So let's group these terms together by using their corresponding factors. So let's focus first on u to the third. So u to the third, so this is going to be here a and then c. So let's put that inside of the parentheses, a plus c multiplied by u to the third. Now terms that have u squared, the first one was minus a square root of 2, so let's write that down inside of the parentheses, so that is minus a square root of 2. The next one is plus b, then I also have plus c square root of 2, and then I have d. So u squared is common to all of these terms. Now terms that only have u, first one is a, then I have minus b square root of 2, then I have c, and finally I have d square root of 2 u. And finally the independent terms, which are b and d respectively, so that is going to be b plus d. So all of this is equal to u squared. Okay, so what can I infer from here? For example, if I first look at terms that have u to the third on the left side of the equation and on the right side of the equation, I can see that u to the third, I have u to the third here, but I have no terms with u to the third here on the right. So what I can say is that the sum of the terms inside of this parenthesis should be equal to 0. What happens with the u squared? Here I have this term that multiplies u squared, and on the right I have u squared, so the coefficient here is 1. What does that mean? That the sum of these terms inside of this parenthesis should be equal to the coefficient of u squared on the right, which is 1. So this sum is going to equal to 1. What do I have here regarding u? So I have this term that multiplies u on the left, but I have nothing on the right that has u, so this sum of terms is going to be equal to 0 as well. And same thing for the independent terms. Since I have no independent terms on the right, meaning I have no numbers, so b plus d is also going to be equal to 0. So in this way I can build my equation system. And the first thing I will say is that a plus c is going to be equal to 0. Now let's focus on this other term, on this expression. So minus a square root of 2 plus b plus c square root of 2 plus d is equal to 1, we said. So that is 1. Next, a minus b square root of 2 plus c plus d square root of 2 is equal to 0. And finally, let's look at this last set of expressions, and that is b plus d is equal to 0. Alright, so at this point I can already derive some things. For example, I can say from this first equation that c is equal to minus a, and if I look at the last equation I will say that d is equal to minus b. Just for convenience, I'm going to label these two equations 1 and 2 respectively. So let's first operate on 1. So we're going to operate on 1. Alright, so if I do that, I will have that this is minus a square root of 2 plus b, but I know, okay, let's just copy that over. Plus c square root of 2, but I know that c is equal to minus a, so let's replace that here. C is minus a square root of 2 plus d, but I know that d is minus b, so let's also replace that. Minus b is equal to 1. Now let's do the same thing on the second equation, and the second equation is a minus b square root of 2 plus c, and c is again minus a, so let's replace that, plus d square root of 2, but d is minus b, so let's also replace that, and that is equal to 0. Okay, there are things that will cancel out here. For example, on the first equation, b and b will just go away, and on the second equation, a and a will also go away. So what I have for the first equation is the following. So minus a, that is minus 2a square root of 2, and if I solve for a, I will have minus 1 over 2 square root of 2. And here I will have the following. I will have minus b, that is minus 2b square root of 2 is equal to 0. Therefore, I can say that b is equal to 0. Alright, so I can easily solve for the other terms. For example, c is just a with negative sign, so I can say that since a is minus 1 over 2 square root of 2, then c will be equal to 1 over 2 square root of 2. And I can also solve for d. Since b is 0, then d will also be equal to 0. So let's state the solution for this equation system. So I can say that a is equal to minus 1 over 2 square root of 2, b is equal to 0, then c is minus a, but since a is this expression, then c will be the positive of that, so that is 2 square root of 2, and then d is minus b, but since b is 0, then d will also be equal to 0. Okay. Now, Since I already know the coefficients for my decomposition here, what I need to do is I need to replace these coefficients in this decomposition. So let's bring that up here. I can say that I1 is equal to integral of, it was AU plus B in the numerator here, but since A is minus 1 over 2 square root of 2, I will just write that down here. So that will be minus 1 over 2 square root of 2 U plus B, but since B is 0, then I'm not going to write it down. I'm just leaving that out. And the denominator for that was U squared plus square root of 2U plus 1. So let's copy that over here. So this is U squared plus square root of 2U plus 1. So the other expression was CU plus D, but I know that D is 0 and C is 1 over 2 square root of 2, so let's just copy that here. So that is plus 1 over 2 square root of 2 U over U squared minus square root of 2 U plus 1 du. Okay, so at this point there are some terms that can be factored out. For example, 2 square root of 2 is common to these two terms, so I can get this expression out of the integral, and I can also swap the two terms that I have inside of the parentheses, because the first term is a negative expression, so I can just swap this for better convenience. So let's do that. First, I will factor out 1 over 2 square root of 2, which is common to these two terms, and what I have inside of the parentheses can be swapped. So let's first write this second term, that is U over U squared minus the square root of 2U plus 1, and then the first term here, the one with the negative sign. So that is minus U over U squared plus the square root of 2U plus 1 du. Alright, so what can I do in order to solve for the integrals that are inside of the parentheses? I can apply some strategies. For example, I would find it convenient to make the numerators look like the derivative in the denominators. In that way, I will be able to evaluate the integrals more easily. So if I take a look at the derivative of this first denominator, for example, what I should have after applying the derivative is 2u minus the square root of 2. So what do I need to do for the numerator to look like that, to be 2u minus the square root of 2? I need to multiply and divide by 2 first, and then add and subtract some terms here, particularly square root of 2. Let's do that. So first thing I'm going to do is I'm going to apply a multiplication and a division to both terms I have inside of the parentheses. And the term I'm multiplying and dividing is 2. So on the numerator I will have 2u, and the denominator should also be multiplied by 2. Since I am multiplying the numerator by 2, then the denominator needs to be also multiplied by 2. In that way, I will not be affecting anything here. So let's do that. Okay. And then I will do the same thing for this other term on the right. So that is 2u over 2 u squared plus the square root of 2 u plus 1 du. Okay, so as you can see, the term in the numerator is starting to look like the derivative of what I have in the denominator here. So in the denominator, I have u squared, so it will be helpful for me to have a tu in the numerator. Let's continue with the process. So here, 2 and 2 are common to both denominators, so I will just factor that out. And okay, so 2 multiplied by 2 is 4, the square root of 2. Integral of 2u. So what I'm going to do right now is, since I also need a square root of 2 in the numerator for this to be equal to the derivative of what I have here, I will add and subtract minus the square root of 2. So let's do that. So the numerator is going to be this, and the denominator is u squared minus the square root of 2u plus 1. And same thing here. Since I need a square root of 2 in the numerator, then let's add and subtract that term. So that is 2u plus the square root of 2 minus the square root of 2 over u squared plus the square root of 2u plus 1. Du. Okay, let's now reorganize the terms I have here. So I'm first going to copy this over. And I want to group this such that I only have the derivative of the denominators in the numerator of these expressions. So first I will have 2u minus the square root of 2 over u squared minus the square root of 2u plus 1. And here I will have 2u plus the square root of 2 over 2 over u squared, square root of 2u plus 1. And since I have added and subtracted the square root of 2 here and here, I need to separate those two terms. And yeah, so here this will be plus the square root of 2 over square root of 2 u squared, the square root of 2 u plus 1. And here I have minus and minus, that is plus the square root of 2 over u squared plus the square root of 2 u plus 1 du. Well, what you can see here is I can evaluate the integrals of these first two terms inside of the parentheses, and if I do that, I will get that the integrals of these two terms are just the logarithms of what I have in their corresponding denominators. So what I'm going to do right now is I'm going to distribute this integral that I have here to all of the terms inside of the parentheses. And if I do that, I will have the following. So this is going to be 1 over 4 square root of 2 integral of 2u minus the square root of 2 over u squared minus the square root of 2u plus 1 minus integral of 2u plus the square root of 2 over u squared plus 2 square root of 2u plus 1 plus, well, this is a constant, so that will be out of the integral here, du over, actually, I am forgetting something here, so this should have been like this, and this one also. All right, so, okay, I will have this over here, plus the square root of 2 integral of du over u squared plus the square root of 2u plus 1. All right. So these first two integrals will be the logarithms of what I have in their denominators. So let's write this again. So this first integral is just the logarithm of what I have here in the denominator minus the square root of 2u plus 1, and same thing here. So this integral is just the logarithm of the denominator, which is u squared plus the square root of 2u plus 1. Okay, so how can I corroborate that? If I apply the derivative of this term, I will have that derivative is 1 over u squared minus the square root of 2 plus 1 multiplied by the derivative of what is inside of the parentheses, and that is 2u minus the square root of 2, which is exactly what I have here on the numerator. And same thing here. So now you can see why I found it useful to add and subtract terms and then multiply and divide by 2, because I needed to come up with these expressions so I could evaluate the integrals more easily. Okay, so I have already solved part of the integral. Now I need to focus on these two integrals I have here on the right. And just for convenience, I'm going to name those integrals y1 and y2 and y3 respectively. So that is going to be square root of 2 multiplied by I2, and I2 is going to be this expression for me. And this. All right. So I will say, therefore, that I2 for me is the integral of du over u squared minus square root of 2u plus 1, which is this integral I have over here. All right, so how can I solve this integral? What I can do here is I can apply a substitution such that the denominator of this expression becomes the sum of two squared variables. In that way, I will be able to apply a trigonometric substitution, and I will make this integral easier to solve. So let's write down what I have in the denominator over here. The denominator is u squared minus the square root of 2u plus 1. And I can also write that like this: u squared minus 2u multiplied by a square root of 2 over 2 plus, and this one can be broken down like this: 2/4 plus 2/4. All right. So why have I done that? Because I want these first three terms to form a squared binomial. So I can write that expression like this as well. So this is going to be u squared minus 2u square root of 2 over 2 plus, and I can write this as square root of 2 over 2 squared, and this other term is going to be square root of 2 over 2 squared. So what I have here inside of this parenthesis can also be written like this: u minus square root of 2 over 2 squared plus square root of 2 over 2 squared. And that is what I was looking for. Okay, so let's replace this here in I2. So I2 is going to be integral of the u, and this first term is going to be y minus the square root of 2 over 2 squared squared. Okay, so at this point what I can do is I can apply a trigonometric substitution in order to solve this integral, and that is what I'm going to do. So I'll say that u minus the square root of 2 over 2 is equal to the square root of 2 over 2 tan of t. If I apply derivatives to both sides of this equation, I will have du on the left, and the square root of 2 over 2 sec square of t dt on the right. And I will also need to know what the value of t is here. So I also need to solve for t from this first equation. So what is t equal to? T is going to be equal to arctan of, okay, this term will go to the other side as an inverse, so that will be 2 over square root of 2 multiplied by u minus square root of 2 over 2. And t therefore will be equal to arctan of a square root of 2 u minus 1, if I simplify the terms inside of the parentheses. Okay, at this point I already have everything I need, so let's get this replaced in I2. So I2 is then going to be equal to integral of du, but du we know is this expression, so I will replace that. That is the square root of 2 over 2 sec square of t dt over y minus the square root of 2 over 2, but I know that this expression is equal to this. So if I replace that, I will get the square root of 2 over 2 tan of t squared plus square root of 2 over 2 squared. At this point, there are some things that can cancel out here. So what will happen is that I can write this expression like this. So this is going to be equal to 1 over the square root of 2 over 2 integral of sec square t dt over tan square of t plus 1. Okay, by definition, I know that sec square of t is exactly equal to tan square of t plus 1. So what will happen here is that this term with this other term can cancel out, and I will have that I2 is then equal to square root of 2 t plus c. So if I solve for t right here, what I will have is this as a function of u. So I2 is equal to square root of 2 arctan square root of 2 u minus 1 plus c. Alright, so I have already solved for I2 now. If I follow a similar procedure for solving I3, and indeed you can do it yourself, just for verification, I will get that I3 is equal to square root of 2 arctan square root of 2 u plus 1 plus c. Alright, so at this point I have solved for all integrals I need. So just for convenience, I will I will go ahead and copy this expression I had originally here. I will just not write it down entirely. So let's copy this over. Okay, there it is. Okay, so at this point, what I need to do here is I need to make the necessary substitutions for I2 and I3. So let's do that. So I1 is going to be equal to 1 over 4 square root of 2. And the difference of these two logarithms can also be expressed as a single logarithm of the division of what I have inside of the parentheses for this logarithm. So that is going to be u squared minus 2 minus the square root of 2u plus 1 over u squared plus the square root of 2u plus 1 plus the square root of 2 by I2. But I know that I2 is this expression here. So what I will have is square root of 2 multiplied by square root of 2 arctan square root of 2u minus 1 plus square root of 2 multiplied by I3, but I3 is this other expression. So that is the square root of 2 arctan square root of 2 u plus 1 and then sorry, everything here plus c. Okay, so at the beginning I made some substitutions. The first substitution was that u was equal to the square root of tan x, and then I was equal to 2 times I1. I will write those expressions down here again, just for convenience. So my first substitution was the following. I said that u was equal to the square root of tan x, and then I is equal to 2 times I1. So in order to solve for I, what I need to do first here is I need to multiply this expression by 2. So let's do that. In order to solve for I need to multiply this by 2. So that is going to be here 2 and 4 that is 1 over 2 square root of 2. Then I have the terms inside of the parentheses, so I will have the logarithm of u squared, but u squared is in this case tan x, so tan x minus square root of 2 u, which is square root of tan x, so that is square root of tan x plus 1 over y squared, which is again tan x plus square root of 2 tan x plus 1. So this is 2 R10, and what I have inside of the parentheses is square root of 2u, and that is again square root of 2 tan x minus 1, and then here 2 R10 square root of 2u, and that is square root of 2 tan x plus 1, and plus the final constant. So yeah, this is the solution for this integral. As you can see, at the beginning it looked pretty straightforward to solve, but actually we had to follow a series of steps in order to get this solved, and yeah, it ended up being a bit tedious. But I hope you found this video useful, guys. I'm looking forward to creating more videos like this. So if you have any comments, please let me know in the comment section of the video, and thank you very much.